Here we go. So we're going to start the other big branch of calculus today, which is integration. So this is like the other 50% class, kind of like. So we're just doing an intro, what is integration, and that kind of thing today. And we've kind of done a little bit of integration. We just didn't know it on a couple problems in the past. So I want to try to motivate it by talking about those kind of problems first. Okay. So our goal first is to try to find a function. Now we're going to call this function capital F of x. Now I personally always kind of had trouble with that notation, but you do kind of need it. So I'm going to try to avoid that notation whenever we can, because I bet you guys will find it confusing. But we're going to try to find this capital F of x, whose derivative is, it's the only thing we need to worry about for capital F of x, is that we make sure its derivative is 3x squared. Okay? I'm going to do a little side note. So this is my little side note. I think it's easier
or x cubed
to find f of x if you think f prime of x equals 3x squared. So if you want to think in that kind of a way, then by all means feel free to do so. I need this capital F for a couple little things here and there though, so that's why I'm introducing it. And also, I mean, if you took this class, if you took a calc class in college, you'd want to have seen that. You know,
wait, so is that like
the professor's probably not going to be nice like me.
I have a question. Is that like capital F of x in the blue?
In here, the blue, no.
Okay.
The blue's where I got rid of it for you. So personally, I think it's easier to think like in the blue. So if you have to make the derivative 3x squared, right? What is f of x to begin with? X cubed, right? So you guys came up with it. So you're saying if you do x cubed is capital F of x, or regular f of x, if you think of that as x cubed, then you take the derivative, right? You take the derivative of x cubed, and you get 3x squared, like it's supposed to be. So you were able to guess the antiderivative there, because that's what that is.
So the antiderivative is?
Yes, so the antiderivative is this capital F guy. So capital F of x is called the antiderivative.
So it sounds like the original.
It is, it's like the original thing, but it's the process of, instead of differentiating forward, it's kind of the process of going backwards. And you might say, well, why does that matter? Well, it turns out that that has like a lot of other different physical interpretations than a tangent line does for a derivative. Okay? So it might seem really easy, and it is kind of nice, because all those derivative rules that you learned, most of them, not all of them, but most of them go backwards. And it's just the backwards process. So it's not like you have to learn a whole new library of them. Okay? So this is called the antiderivative. Of f. It's the antiderivative of f if you take its derivative and you get f of x. And technically, this is a little technical thing, we won't need to worry about it in this class, but it's for if you can do that for all x in a specified interval. Why am I saying that? Well, we won't have to worry about it in this class at all, but in advanced like computer math and so forth, like any kind of advanced applied math, sometimes you need to find these antiderivatives. If you kind of with me on that, you need to find an antiderivative to accomplish some purpose, and you might not, there might not be one. Some antiderivatives just don't exist. Derivatives always exist, like they always, we did tons of them, right? They always work pretty easily. You guys might have had trouble with some of the bigger ones, but they still come out, you know what I mean? When you go backwards, some of them don't exist, period. But see, you can make them exist maybe for just a part of the number line and solve your problem that way sometimes, and I've done stuff like that in advanced math before. So that's why this little part's on here. Let's not worry about it though. Okay. So I have a question for you. That example that we did to start out, the one where you guys gave me x cubed, is that the only answer you could have given me?
I'm sure. There's a product rule probably you could.
No, don't think too hard. Is there another possible antiderivative for that f?
Wouldn't it be something over neg?
X
or
cubed
no?
plus 1.
Wouldn't it be like
How about this? I'm going to call that f1. How about f2 of x equals x cubed plus 1, like Cassidy said? If you take the derivative of that, what do you get? 3x squared, right? That just goes away. So does that count? Yep.
Plus any constant. So
Yep. So you could go x cubed
Plus
minus
k.
square root of 7 or square root of 8, right? Anything.
plus or minus c.
Yeah, and that's the idea. So the antiderivative, let's write that down. It's plus or minus any constant. Excellent. Plus or minus c. That's the one we used to. Very nice. You guys are on it. It's not that hard of a concept. So there is always an infinite number antiderivatives. If you can find one, sometimes you just can't find one, but if you can find one, there's always an infinite number of
Always
them.
add a constant.
Yeah, exactly. An infinite number of antiderivatives found by taking the antiderivative and going plus some constant. We don't say plus or minus because the minus can be absorbed into the
By a
constant.
negative.
Yeah, the constant, you can just call it a negative and that counts as the minus. Okay? So let's do our first little foray into differential equations. We'll have a chapter on this later. I think it's actually a pretty easy chapter because we're not going to do any hard differential equations in this class, but let's solve our first differential equation. These are the most basic differential equations you could possibly have. We've verified them in class before, but we've never solved them. We're not going to do too much of that in this chapter. We have to wait a little bit. Okay? And I love differential equations. Whenever they, and guess what? The new theme, the new trend in AP tests is that they almost always have a whole free response question that's a differential equation. And when I see that, I'm like, score! We can do this one. You know what I mean? So, anyway, there's a differential equation. Because it has a derivative in it, yeah? So there's one. Let's do another one. So,
Would it just be capital Y? Is that how you'd write that notation?
nope, this is how you write it. It's like lowercase y prime. Okay? So when you're solving a differential equation, your goal is to come up with the original function. Yeah? So I think for us, that's really just good, since this is so simple, it's just going to be the antiderivative. So what's the antiderivative here? What is y? 5x. Now, that's the antiderivative. Once you add the c, this whole thing right here
Is the function.
is this part's the antiderivative. The c is what we're going to call, this is the general solution. So if they ask you for that, that's what they're talking about. This is the whole family, the infinite family of curves that satisfy that differential
You
equation.
specify that
Okay.
c equals any.
You can specify, and they will be doing that real soon, once we get to differential equations. Usually, you nail C down by some kind of thing called like an initial condition, but we'll do that later, okay? So right now, we're just gonna call that whole thing, this is the antiderivative. When you add C in, that's the general solution, or you might say the family of solutions to the equation specified right there. Okay, so can you guys help me solve that other one? Did that one. This is y. This is really a y of theta, so I'll write it like that.
Yeah.
What is it?
Negative cosine.
Negative cosine? Is everybody following? Negative cosine? Why? If you wanted to check, could you check real quick? You could check real quick. Take the derivative of that. Did you get sine? Yeah, because negative sign is easy, right? I could write it down, but I'm not going to. You guys seem comfortable. Okay, so
In our answers, do you want us to put plus c?
So they should
All
get
of
the
them?
C.
Excellent question. So, like on the AP exam, if it had asked you, it depends what they ask, right? If they ask you for the general solution to this differential equation and you left off C, it'd be completely wrong.
You need.
So that's plus nothing. So you always have to have the C. If it, pretty much you always have to have the C. Good question.
Yeah, they just put it in
there.
There will be times where we don't have a C, but I will show you those in a few days. Okay, so you'll know clearly. It's very easy to tell whether the C is needed or not. Okay, it's not a hard thing. For right now, C's. Excellent. Okay, so let's just think back. So let's say we have that differential equation. I want us just to contrast some of the different stuff that we've learned, and it's going to help us understand how integration and differentiation relate to one another, okay? So that's just like a little differential equation, right? It says dy dx equals f. So if you move that dx to the other side, we've done that before, haven't we? You know what the name for that is? This is what form?
Isn't that like the approximation?
It's in that. It was in that section. Yes.
linear
Summation.
approximation.
It was in that section, but it was the other thing.
It's the O.
This is the differential form.
Sure.
Is anybody uncomfortable with what I did there? Did I do something like drastic to get from one form to the other? What did I do? It's like I multiplied the dx up. Like nothing spectacularly crazy happened. There's some deep ideas behind this though. So now, what I'm going to do to both sides of that equation is I'm going to introduce new notation. You've seen this symbol before, right? Is it on the front of your book? Oh, it's not on the front of our book. Most calc books always have this symbol because it's the most famous calculus symbol on it. Okay. So that symbol is the integral. So integration has lots of different meanings, just like derivative had lots of different meanings, right? Derivative could mean velocity, could mean slope of the tangent line, could mean other things. You didn't see it a lot more than that. That's the second derivative, right? But it has these different meanings. Integral likewise also has some different meanings for sure. But all it is it's an operation. Can you differentiate both sides of an equation? Yeah, we didn't do it too much, but you can do that. Likewise, you can integrate both sides of an equation. That's all I did here. The question is, what do you get when you integrate that? When you integrate a derivative, you get the original. They undo each other. They're kind of like inverse operations. Like square root gets rid of x squared, integral gets rid of derivatives. Okay, because one's forward and the other one is backwards. So integral is just like
so
the
you operate with integral kind
yes,
of?
exactly. I love to think about it like that. So when you integrate f, you get its antiderivative plus c. Exactly. Okay, so it is how these are working together. They're starting to make sense kind of as a theory. It's not like a super hard thing. So all we're going to do for the rest of today, I should probably note that differentiation for our notes. You're going to know this inside and out, but differentiation and integration are inverse operations. They're just the most advanced operations you've ever seen. Okay? Okay, so I want us to open our book real quick to page 250, if you would. And then we're just going to do some examples. Most of them are just things you know already backwards. There's some exceptions. So we'll need to know a few new rules, but not too many. If you know your derivatives really well, it's not too hard to go backwards. But there are some things that we have to do that are different, for sure. 250. 250 has all the basic integration rules, and I think these would mostly seem familiar to you. There's not any sneaky ones yet. Okay.
What does it do with integration? What does this have to do with integration? The sound barrier, the jet. Okay, just curious. That's all I'm at.
It has a surface. Anything with a surface has to do with integration.
I don't understand where that comes from exactly.
Anything with a surface or arc length has to do with integration.
Where does the sound barrier come from?
Like this. Whenever they pass it, it's like.
it's just the surface. As you penetrate that surface at a certain speed, like it's like you're, I don't know how to explain
So
that super
normally
well.
you
It's like you're
Shattering it?
it's like something about your velocity catches up to yourself, and you like smash. That's
so
not
they
very
kinda-
good. Yeah,
okay.
and that's
Like
what the sound
Superman
comes from.
trailer.
Is that a thumbnail?
That's not a very good explanation, but I could do better if I
You
looked
can
it
hear
up.
it probably,
Okay, let's look at the rules. I want you to look at that table on 250,
Yeah,
because those are all
actually,
rules you're responsible
N is a
for.
little bit weird looking.
Oh my God.
It's
I mean,
easy
not
to
weird,
use,
weird.
really easy to use.
I don't understand.
So let's see if we recognize those rules.
Oh yeah.
Do they seem familiar? I think all those ones should seem
A
familiar.
lot of them just look like derivatives.
It's just backwards.
Oh
I just don't understand why they get from this to this.
yeah. That's an integration. It's a differentiation.
Yeah,
So
they're
little-
different, but I just don't understand.
Yeah, these are all ones that we should know. The only one that might look different is the x to the n thing, and that's what we're going to start with. So all those other ones are just taking what you know and putting it backwards. Okay? So you should feel good about this, because if you know your derivatives, it's not like you have to know new stuff. There are some new ones, but there are not that many. And not
chain
today.
rules and stuff, you basically just apply it.
Chain rule is a problem.
Chain rules is a
Integrating
problem.
stuff with chain rule is a problem, and that's
So
where
do we do that?
the main bulk of our time during the second semester will be spent.
So we're not doing that now then?
No.
I don't understand how, like,
I'm very good at teaching that, though. That's probably the thing I'm best at teaching out of anything, is how to undo the chain rule. So I've done it for so long.
honestly, I don't understand how, like, you get, like, this side from this side, like,
That's all.
I know they're different things,
Okay, let's do some examples. So we'll keep those rules in mind. We'll do these. I'm just gonna not even write numbers on them. I don't want numbers in the way.
but well, I understand what that is. I just don't understand how you get this. No, I know they're different things. You don't get them into, like, I have any slide.
Notice, what do all these integrals share? You always have the dx on them. If you leave that dx off, that's a thing that it's like a flashing I don't know what I'm doing to a grader. Okay, so leaving c's off, leaving dx's off, that's like a I don't know what I'm doing, and I'm gonna show that to you, and you're gonna know I don't know what I'm doing. Okay. So how do we integrate these? Notice, one of those integral rules says if you have a constant in front, notice, what do we do with constants when we're doing derivatives?
We just put them off.
We just kind of put them off to the front, and that's exactly what we're going to do when we do integrals, just put them out in front. And that should make sense, okay? Now, when you do the integral of x, what do you do?
Isn't it?
Think about it. If you want the thing that's backwards from x, anybody got a guess? Don't use the rule yet.
1.
You're not going forwards, it's not 1, that would be
It's
the
x
derivative. The
squared.
integral is going to be backwards, which
So
is
0.
x squared something,
But it's
right?
gonna have to be over something because you have a 1 right there.
It's going to have to be over something, exactly.
So it's x squared over 2.
So the rule says this, right? Your rule in the book says that the integral of x to the n, does it say that?
Yeah.
It says it's x to the n, and instead of
Plus
subtracting like for derivatives, you add, and then once you've got that, then you divide by that.
Which makes sense.
That's how you go backwards. And you could have figured that out yourself. I mean, I was kind of trying to help you guys figure it out yourself. That's all it is, though. Don't make it hard. So this is going to be 3. If that's 1, then it's going to be x squared, but you divide by the 2.
Plus c.
Plus c. Don't forget your plus c. Excellent. So that's 3 halves x squared plus c.
Wait, I don't understand where you got the x squared
Plus
I have to get
1x.
1 plus 1.
from. Oh, okay.
So the rule says instead of subtracting 1 like you did for derivatives, you add. Okay? So then, what do you guys think I should do for this one?
X to the negative 5.
Remember, that's what we did with derivatives. We rearranged it so we could see it. So you go 7 integral, I put the 7 outside, x to the negative 5 dx. Don't forget your dx's on those steps.
So it'll be
You want to flag someone that you're a fool?
4 or get to the negative 4.
It'd be negative 7/4 x over 6 x to the 4th.
What is this? Negative what?
4.
4, then divide by that. Don't make this hard, okay? Just do it one step at a time and then simplify afterwards. I hear you guys trying to do it all in one step, which is fine. You'll get to that point, but... Oh, what did I forget? Plus c, because there's an infinite number of things that could work, right? So now if you take the derivative of that, remember the whole point of this is if you take the derivative of that, what are you going to get?
That.
And that's the point. Okay?
How do you get dx from that though?
You'd get...
Oh, okay.
Good question. dx is like something that always goes. These symbols always go together. Okay? And that has to do with that. If you're unsure about that, go back to where I derived how the integral worked and how we multiplied the dx up and stuff. And that'll make sense to you a little bit more. Okay, this one. How should I do it? I should say the integral of x to the 1/5 first. And then that's going to be x to the 1/5 plus 1. Oh, I love you guys. 6/5. So this is going to end up being, flip that fraction, 5x to the 6/5 over 6 plus c. Clear? Not bad. Let's try something a little more interesting maybe. Actually, I want you guys to try this one. See if you can do this one now. I'll give you a few minutes. See if you can do... What is that?
Yeah, I guess.
And you know, of my two operations, I love integrals. I think you guys will come to like them too. They're even more powerful than derivatives. They can do so many things. I was intimidated a little bit in high school because my teacher taught the Zen method, but I will show you guys many different ways to do that. Yeah, I wasn't too zen-y.
Will we share what it was?
Yeah, I'll show you how to do it that way too. But you may like it. I think you're gonna like it the other way, okay? I think Todd's gonna like it.
Probably.
Maybe not.
I was just curious.
Do one piece at a time, right? Remember one of those properties on your chart says if you have more than one integral, plus or minus in between, just separate them.
Oh, should be times 4. Yeah, it should be times 4. But I did the rest right.
There's the technical nice way to write it. You're probably going to start skipping that step soon, but that's why you can do this. You guys see all I did is I split it up into 3 different integrals because you can do that with multiple terms. Anytime you have multiple terms, you split it into multiple integrals. That's really key. Sometimes one of these terms will be a lot harder than the others, and you have to focus on that one. Okay? So then I pulled my constants out front at the same time. What do I get for the first term?
X to the 5th over 5.
Okay. Somebody else help me with this one. Austin, can you help me with this one?
I had 2x to the 4th over 11 times 4. So 44.
Great. And somebody else? Oh, we know that one. That's too easy. What's it simplify to? Soon you're going to do this in your head.
I said 2x squared.
2x squared. Maybe not yet, but soon I'm sure you'll all be doing that in your head. And then I want... I'm done. So, any polynomial, easy. So polynomials are easy to integrate. Unfortunately, the vast majority of stuff is not a polynomial when you need to integrate it. Darn. So let me show you this one. This integral right here is the first of its kind that you're going to see. And the more you take my advice, I think the better you will be at integrating.
Can you rewrite that?
I got to where I could always do any integral that was brought to me from Calc 1, 2, 3 and above. I could do them all in 30 seconds and teach them. Most of the professors couldn't do that, and I'll show you my method, okay? So there's some good hints I have for you. So if you have a rational function like that, you always first want to, sometimes we're going to have to use identities, sometimes we'll have to use different techniques to get this bottom to one term. If you can get the bottom to one term, you're probably victorious, because then what can you do with the integral?
First integral is.
Would you do like
You can like common denominator it and split it up and it breaks down nice. Okay.
Could you make that x to the 1/2 and then bring it up to the top?
You could.
Okay.
But what I want us to focus on is once we can get a one-term thing on the bottom, we're going to win, no matter how hard the integral is. Okay? That's one of our goals. So we've got a one-term thing already in this one. Sometimes we'll have to do that, but now you just break it up. I know most of you guys are in fact, all of you guys are very good at doing that. So why have I trained you to do things that way rather than another way? Well, it's because of this.
You should have parentheses or something.
I should, technically. Not a big deal, but. And now you reduce, because once this happens, usually you'll be able to reduce or do something else. Okay? So here, how's that reduced? This is 1/2. So 1 minus 1/2 is 1/2, right? And then that's going to be what? This is also 1/2. So this is x to the. Don't make it hard. Negative, right? It's underneath. Negative 1/2. Make sense? And then those are both easy. So you go x to the 3/2 divided by 3/2 becomes
2/3.
2/3. If you want to do that in 2 steps, do it. This one becomes plus negative 1/2 plus 1 is 1/2 divided by 1/2
2x.
becomes 2.
Wasn't it negative 1/2 on the top? Just like
Plus 1.
Add 1.
Oh, add 1. Oh, okay.
And it becomes that, and then you divide by 1/2. It's the same thing as multiplying by 2.
Got it.
Yeah. If you want to take both the steps, do it. I'm just showing you how you can eventually get there. Okay. And of course, plus c. And if you want to change that to square root of x and stuff, you can. You can write this. The book might write this as 2x root x over 3 plus 2 root x plus c. I don't care. Okay, let's do one with some trig in it, because we've got all those trig ones. I'm just going to do one, and then I think you guys will get one. There's not too many hard ones in there. So you might need to do something like this. A lot of integrals are going to have options. You're going to have to try different things. So I think this is a simple example of that. Do we know, like, sine over cosine squared of x? Is there like a formula for that on your gray sheet, for instance? Is that a derivative? Ask yourself, is this a derivative that you recognize?
No.
I don't remember us learning that
So would you
derivative.
like
Secant
hide it a
squared
little
sine
bit differently?
x.
Yeah, you don't have to worry about the quotient rule really too much in reverse. Good guess, though. Good guess. Good thinking. So what else? How else could we change that around? There's different options we have. We do
So
this.
the bottom be cosine times
You can make this one on the bottom.
cosine times.
You can make a cosine times cosine. All right, let's do that. So could you do this?
It's tangent times secant.
And then Anna says, well, if it's that, that's just tangent times secant. Notice I'm not telling you guys what to do, which is what?
Secant. Secant squared. Yeah, it's secant squared.
Whose derivative is this sitting here?
Secant.
Secant. Done. Another option we might have considered if that didn't work was what? Changing that cosine squared into what?
Secant squared.
No.
No, you don't want to do that.
What else does
Plus sine
cosine?
squared.
Yeah, 1 minus sine squared maybe, and then we could factor it apart and stuff, and we'll do ones like that soon.
Oh.
I don't think there's too many like that. So if you see this, you want to think about doing that, or maybe doing 1 minus sine squared using the identity, those kinds of things. Okay? I think we're done. I think that should get you through what you need.
Caitlin?
Okay, so we're gonna do this guy for Monday.
Oh, wait, no. I already have it
Okay, so that seems like a lot. I think most of these, as you've seen, are pretty darn fast, so I don't think it's really going to be that big of a deal. There's no real hard integrals in here. Maybe there's a couple medium ones. That's probably all.
This was optimization.
No.